before you can put it into the equations, you need to start assigning all your different forces acting on these objects. And that's where free body diagrams come in. So I've got a few examples here. I remember when I started doing this, it all seemed like magic, but the more you do, the better you get. There's no trick to it, just to practice, practice, practice. So in this situation, if we want to do a free body diagram, we have, well, first off, we always represent the mass at its center of gravity at a point. So we just model it. We're going to say this mass at its center of gravity is this point now. And one of the forces acting on it is the force of gravity, pulling it downwards. So in our free body diagram here, we represent that force of gravity, and it is a vector because it has a direction. And then perpendicular to the surface here, you're always going to have the normal force. And the normal force is a very common one because it needs to counteract a lot of the force of gravity pulling down. And so the normal is always just perpendicular, so at 90 degrees to your surface. And then we have a few other forces here acting on this object. We have the force of static friction, S for static friction, which is preventing this block from sliding downwards. So the force of static friction. And there's two kinds of friction. This is an important thing to distinguish. So here we're going to model our second situation now. We have our center of gravity, point of mass, and it has, again, the force of gravity pulling it down. It has the normal force, perpendicular to the surface. And so in this situation, it is moving with a velocity. So in this case, we're going to have friction, but our friction is going to be kinetic friction. We'll represent that with a K. And so you get kinetic friction when you have motion, but you have static friction when that's the force holding it in place, keeping it from moving. So it is very important to distinguish those. Okay, in our next situation, we have our point, and we have a force pulling up. And this is just any regular force. And this isn't moving, so it means we must have a counteracting force of, do you remember? Well, if it's not moving, then it's static friction holding it in place. And then, of course, we have the force of gravity pulling it down, and the normal force counteracting the force of gravity moving up. So in this situation, hopefully this is starting to become routine. You've got force pushing down at this angle. Then it's not moving, so we need static friction force pointing in the opposite direction to help cancel that out. In fact, doing these vectors properly, this should be a bit longer. This vector force of static friction, because it's not moving. So this needs to cancel out the x component of this force here. Then you have force of gravity and the normal force pushing perpendicular up to the surface. Okay, so now we're going to go the opposite direction. So we're going to start with our free body diagram and figure out what's happening in the real world situation. So we know that it has kinetic friction, so it's a moving block or a moving mass, and it's on a slope here, and it's got its normal coming up, and it's got a velocity because you know it has a velocity because it has kinetic friction pulling back this way. And then it's still going to have its force of gravity. So this is all good. And then this is a new one, so a new symbol here, T, which stands for the force of tension. So whenever you see tension, usually it's a good bet it's going to represent a rope. So say we've got a hanging mass and there's a rope which it is attached to. And so this situation, we have the force of gravity pulling it down. Then we have the tension in the rope holding it up. So say this had a mass of 10 newtons, this block here, then we actually know that the force of gravity is equal to mass times the gravitational acceleration of Earth. So the force of gravity will be 10 newtons multiplied by 9.8 meters per second squared. So it will be almost 100. It will be, probably shouldn't use a calculator for this, yes, of course, 98 meters per, oh, sorry, force, these units here are newtons, and it's going to actually turn into units for, and oh, I see what I did here, yeah. Okay, so this 10 kilograms, 10 kilograms, very important units here. So kilogram meters per second squared equals Newton. So it's very important. I'm going to write it up here just so you know. Newton is in units of kilogram meters per second squared. That's how you do the calculation. And so the force of gravity will be 98 kilogram meters per second squared, or newtons, and that means therefore the counteracting force, the tension, will be 98 newtons. Okay, so back to our free body diagrams. This situation, you have, let's say you have a mass and it's on another incline. You've got gravity down, the normal up, and you have a rope with tension pulling it in this direction, and it's not moving, so there's actually something missing here. There should also be static or kinetic friction, or static friction here. So if it was a tight rope pulling it up, then it would have static friction pulling it back this way. But if it was a loose rope, so it was sagging down, it would actually have static friction holding it up. So this is a unique situation, because if this rope is tugging on it, then the force of friction is going to be counteracting that tug, so it'll be moving in this direction. But if this rope is really weak and it's starting to slide down this way, we'll actually get the static friction holding it up. But that's what your situation is going to look like: gravity down, normal up. And then in this case, we have a block, a mass on a flat surface, and you have a force pulling it in this direction. Maybe it's a little happy person, and they are pulling on this this direction, and there's kinetic friction because it's moving, and the normal up, and the force of gravity down. And I guess if it is a rope, just to stay true to our conventions, then we should stick with tension. Okay, hopefully that was helpful. Have an excellent day.